G'day, this is part 3 of the NEET 2021 Unit 3 and 4 exam, as my very professional sign just indicates to you. This is the beginning of the written section. I'm intending to do questions 1 to 10 in this particular video, depending on how many minutes that takes. Let's see how we go. Question 1, excuse me. Okay, so there's an electron in a magnetic field. The magnetic field is pointing into the page, excuse me. And there is also an electric field that is going that way, left to right, indicated by those arrowheads. Okay. The electric field is represented by the arrows. Yes, at any time, the fields are uniform, but their magnitude is able to be varied. Uniform just means they're the same strength all the way through. Gravitational effects acting on the electron are negligible, if I can pronounce it. Figure 1 shows a particular instant of the electron's motion. The electron's speed is 1 × 10⁶ meters per second. All right, so it's going fairly fast. Assume that the electric field strength is 1 × 10⁶ newtons per coulomb, and B is 0 teslas. In other words, the magnetic field is not turned on at this stage. Determine the magnitude of the net force on the electron. Show you're working. Okay, magnitude, not direction. You don't have to worry about the direction of this, just the size. And you're going to use F equals QE. Right. So this is the formula. This is a really easy question. Right. That's the formula for the force on an electron due to an electric field, the charge multiplied by the electric field strength, and they gave that to you here. That's the right units. Put the charge in the right units. It's 1.6 × 10⁻19 coulombs, I think, from memory, and you'll grab the answer. The answer comes to 1.6 × 10⁻13 newtons. Okay, part B over the page. Excuse me. For part B, they turn off the electric field and turn on the magnetic field, right? So assume that the electric field is nothing, magnetic field is 2 teslas. Determine the magnitude of the net force on the electrons. Show you're working, and this one is just this, excuse me, QVB. Charge on the electron, velocity is going, and B is 2 teslas. Again, you know how to do this. Just get the units right and you'll be fine. The answer is 3.2 × 10⁻13 newtons. As I said, I'm going through these a little bit faster. I'm not going to insult your intelligence by making you watch me calculate that. You know exactly how to do it. Right, this one, part 2. Explain. Explain means give a cause and an effect. Right, link the two. Explain using physics principles the resulting motion of the electron while it remains in the region of the magnetic field B. Okay, so the answer for part B, let's have a look at the diagram again. Keep in mind that there's no electric field from the previous part. There's no electric field at the moment, and the magnetic field is on. So it's only the magnetic field that's affecting the motion of this thing. So left hand, it's an electron, right? Excuse me. Fingers down. Hold on. Sorry, I just dropped something. Okay, fingers pointing into the page, right, because of the crosses. Thumb pointing across to the right because over here it says an electron is traveling to the right. Right. So that's where you got the movement of the electron, and your palm ends up being down to the bottom of the page. All right. So firstly, you have to say the force on it is initially downwards, but you also then have to say that because the force is always at right angles to the direction of the motion of the electron, the path that it takes ends up being circular. So you need to have, because it's an explain, you need to have the cause and the effect. You need to say the path will be circular and pointing downwards because the initial force is directly downwards, right, in brackets left-hand rule, but it remains at right angles to the electron's motion. And that's the definition of what causes circular motion. All right. Oh no, part C combines your answers to part A and part B1. Right? Part A had a force going that way of 1.6 × 10⁻13 newtons, and part B had a force going this way of 3.2 × 10⁻13 newtons. I'm just not bothering with the 10 to the minus 13s. And this question says, well, assume that those two things are both on now, instead of one being on and one being off. Where would the overall force on that electron be directed? It will be directed at the vector sum of those two, which is down here. Right? So that's essentially the answer, but drawing it is not enough. We need to find out the magnitude and the direction. All right, pardon me. In fact, we don't have to find the direction. It just says the magnitude. That's very handy. That's one less thing to do. So we need to basically do Pythagoras with this. That's a right angle. Put the times 10 to the minus 13s in, right? And get the answer, right? And it ends up being, what does it end up being? It ends up being 3.6 by 10 to the minus 13. Now, by the way, it's worth noting that the answer, the solution document has a mistake in this. When they've written out Pythagoras' theorem, they didn't square one of these, right? So they've gone the square root of 1.6 by 10 to the minus 13 squared plus 3.2 by 10 to the minus 13, but they didn't put the squared up there. All right, they should have. Just a typo. Okay, you were right, they were wrong. Question 2. A satellite is orbiting the Earth and it has an orbital period of 94.2 minutes. Calculate the altitude of it to 3 significant figures. Okay, whenever you are talking about the period or the radius of something that's orbiting due to gravity, you're using this. You're using Kepler's third law. R cubed over t squared equals gm on 4 pi squared. Some books have that upside down. It doesn't matter. It's the same thing. All right, that is a constant. And that m is the mass of the thing that it's going around. So it's the mass of the Earth in this case. All right. So all you have to do is convert this to seconds. Right? Time is always in seconds, always throughout physics. So convert that to seconds and put that there. Right? Grab the Earth's mass from the data sheet, put that there. Find everything. G is on the data sheet as well, and you're going to solve that for R. Right? The radius, excuse me, the radius comes to 3.2. Sorry. The radius, pardon me, comes to 6.86 by 10 to the 6 meters. It'll always come out in meters. But the question says, what's the altitude? It didn't say what's the radius. It says how far, that's how far is it above the Earth's surface. So you then have to subtract the radius of the Earth from that radius, right, to get its altitude above it. Excuse me. And it ends up being 4.85 by 10 to the 5 meters. Okay, part B, the satellite has moved to a new stable orbit of greater altitude. Greater altitude, higher up. Explain what effect this will have on the speed of the satellite. All right. Because the velocity, if you remember this, there you go. That's the formula for the velocity of something orbiting something else under the force of gravity. Right. Excuse me. Because that's the formula for the gravity, if the radius gets larger, this overall thing, because they stay the same, ends up getting smaller. So the higher a satellite is, the slower it goes, right? The closer a satellite is, the faster it goes. It's the same sort of principle as when water is running down a plug hole and it's sort of doing that sort of spiral down the plug hole. It starts off going around slowly at a big radius, but it's whipping around very fast at a small radius. Right? That happens to anything that's going around in a circle under the influence of an attraction from something in the middle. It's not just gravity. Question 3, we've seen a lot of this sort of stuff lately. Okay, there is a coil that's going to rotate inside a magnetic field. That is a split ring commutator. So it's going to make AC inside. Actually, it's not making AC. It's receiving power from the outside world. So this is not a generator, it's a motor. It's being given electricity, and that electricity is going to make it turn. All right. I'm sure that that's what it all says. Okay. On figure 2, use an S for south and an N for north to label these things. All right. Does it go north-south or does it go south-north? All right. If they give you the battery, you know which way this current is going. Conventional current, the positive stuff, is going out the long stick. And remember that it makes a little arrow that shows you which way the electrons actually go. But I'm going to go right-handed. They've gone right-handed. They're showing you the direction of conventional current, so right-handed. Okay. So they've shown you the direction of flow of rotation of this thing, right? So that side has to end up going up and that side has to end up going down. So because it's just more comfortable for me to have my hand pointing down than pointing up, I'm going to do it like this. All right. So for me to get my thumb pointing that way on my right hand and my palm pointing down, my fingers have to be going that way. If my fingers are going this way, it doesn't work out, right? So thumb has to be following the wire, the direction of the charge on the wire. Palm has to be pushing that side down and that side up, right? So the fingers have to go this way. So that's got to be north and that's got to be south because the fingers point to the south. So north, south. Cool. Do not waste your time making an explanation. Just do it. It's worth 1 mark. All right. Sorry. The circuit has a total resistance of 4.5 ohms. The battery voltage is 6 volts. The coil has sides of 6 by 4 centimeters. The long sides of the coil are the parallel ones, so that's the 6, right? And the magnetic field is 0.1 Tesla. Okay, how many turns does the coil have if a longer side is to experience a force of 0.32 newtons? All right, this is just filling in the gaps of a formula, and the formula is this. The formula is F equals NILB. Number of turns, current going through it, length of the sides that are experiencing the force, magnetic field strength. You've been given everything except that, so it's a simple algebraic solving it. Once again, check the units. These are in centimeters. They have to be converted to meters. Right? That pretty much is the only one that you don't have there. Now, excuse me. The other thing missing, well, that's the only one that you don't have in the right units, but the one thing missing is the current. How do you get that? You get it using V equals IR, because they gave you the V and they gave you the R, right? The resistance is 4.5. Pardon me. Where are we? The voltage is 6 volts, so 6 equals I times 4.5. Right. You can either just solve that one now, or you can just put V divided by R in that formula, and that's what the NEAP solutions sheet did. They just combined these two formulas. Doesn't matter how you do it. That's quite easy. All right. Only worth 2 marks. It's supposed to be reasonably easy, that one. It is 2 steps, but the hardest thing to do there is to convert centimeters to meters, really. All right. Part C is an opportunity to save some time. This is worth 2 marks and it should be done in 30 seconds. This is, it's good to have a look at the solutions here that are suggested by NEAP, because even they do it in point form. Right? They've just done it in dot points and little phrases. They're not writing things out. Please don't use all of that space to do this, right? Let alone go further. Don't worry about paragraph structure and all that sort of stuff. It's not an English test, right? Get on with it. 2 dot points and you're going to get 2 marks, right? Don't bother doing 3. They're only going to read the first 2 if you do 3. So 2 modifications that could be made to the apparatus. There are a few things that won't count here. Speeding it up, right? Rotating the coil faster is not modifying the apparatus, right? Modifying the apparatus is actually changing some of the equipment here. It's doing something to the equipment, right? Replace the battery with a bigger battery, for example. That's changing the equipment, right? Move the, excuse me. Okay, we're making the coil turn more slowly, so okay, changing the battery to a less powerful battery would make it turn more slowly. Taking these magnets further away to weaken the magnetic field, that would slow it down a little bit. All right. Using wire with higher resistance, that would slow it down a little bit. All right. But any one of them, there are 1, 2, 3, 4, 5, 6, 7 suggestions, right, in the solutions, but only do 2 of them. And this is really a chance to save yourself a little bit of time. You should get 2 marks in about 30 seconds here. Further up, there are going to be places where you're going to get 2 marks and it's going to take you 5 minutes. So save time when you can. Okay, question 4 is out of 7 marks, and this is going to take a bit of doing. This is quite a complex one. Any question that has a page of information before they even ask the question is something that you really need to sort of unpack a little bit before you attempt it. Right? It's worth 7 marks. It should take you about 7 minutes. So don't be afraid if you're sitting here reading this for 3 minutes. right? That's fine, right? That's why it's worth 7 marks. They understand it's going to take a while, this one. All right. So essentially, I'm going to summarize it for you because I've just read it. Some students have basically hung a magnet on a spring, and they've sat it there resting, and they're holding it, and the spring is a little bit compressed, right? And then when they let it go, the weight of the magnet, of course, pulls it down, and it ends up stretched like that. At the extremity of its stretch, it is just at the end of a coil that is connected to a galvanometer, which is just something that measures electricity going through it, right? You can alter a galvanometer to become a voltmeter or an ammeter, right? But it's just something that records electricity going through. All right, excuse me. You don't really need to understand what this is even measuring, right? To what, for what, there's no unit there, right? This is more about the direction of the current, this whole question. Okay, it says when the magnet is released, it oscillates between that position and that position. That's as far down as it gets, all right? The galvanometer needle remains vertical when no current passes through the coil, through that coil. Right? The needle swings left if current passes into Y and out of X, and it swings to the right if it passes into X and out of Y. All right, in other words, it goes left when the current's going left on the inside of it, and it goes right when the current is going to the right on the inside of it. So that's what's going on. So knowing all of that, here's the question. This tends to intimidate people. 4 marks, lots of lines. The magnet moves from the position in figure 4 to the position shown in figure 3. Does the galvanometer needle swing left, remain at 0, or swing right? Explain your answer. Okay. I've drawn it here. Let's go through this. I'm going to give you a different way of answering it to the way that NEEP has given you in the solutions. Right? The solutions are about that they've used a flux-based argument, which is fine if you understand it, but I think, in my mind, I think this, what I'm about to show you, is a little bit more reliable. Okay. I'm going to use the right-hand rule to answer it for a charge that is sitting right there. Now, because this question is talking about current, right? Let's see. The needle swings left if current passes into Y through the galvanometer, blah, blah, blah. It's not saying if electrons pass that way. We're talking about positive current, so we're going to be going right hand. So we're assuming that that thing is a positive thing that's going to move. Excuse me. I'm just going to zoom that in a little bit. Just hold on a second. Okay. All right. So we're going to use the right-hand rule. Now, there's the magnet at its lowest position. That's a north pole. Now, north poles of magnets have a magnetic field around them that looks a little bit like this. That's a north, that's a south. You've seen this 100 times. I'm not going to bore you too much, but it does this. Right? North comes out that way. I'm going to get a pen that works. Sorry. There you go. And they do this, spread out. So out here, they're going roughly horizontally out from the middle. Up here, of course, they go back in to where the south one is. So you started seeing that in about grade 6, so you must know that well. Now, superimpose onto that this. And you get those coils, those red coils that I've drawn, are sitting about here. And that charge that I've drawn, that positive charge, is about there. Nothing else matters about this diagram except that little environment where the charge is. We're just worrying about that. Right? And in that position, magnetic field lines are going that way. So that's what I'm going to draw on my diagram. Okay. And then I'll show you how to actually word the answer in a minute. But I'm going to explain the answer to you first. Okay. Magnetic field lines are going that way where that charge is. However, When this magnet starts moving up because the spring is going to sort of jerk it back up, right? Those magnetic field lines are bodily going to do this. They're going to go up. That is essentially the same as moving the charge downwards through a stationary magnetic field. All right. So we're going to use the right-hand rule to figure out where this thing gets forced. Right? There is a magnetic field that way, right? And the charge, for all it knows, is moving that way down through a magnetic field that is going this way. Right? So it will experience a force into the page. So because it's being forced into the page, and every other charge out here is going to be forced into the page. Right? It's going to start a current going through this coil. And just for good measure, if you want to try something on the other side, if you want to look at another charged particle over here, there's one there. On this side, of course, the magnetic field lines are pointing the other way because it's over here. Right? So you can do that same right-hand rule thing over here as well. And this time, I'm going to have to get out of my chair to get my hand in the right position. But charge going down, because in reality the magnetic field is going up, but that's the same as the charge moving down. Right? Charge moving down, magnetic field lines going that way, it's going to come out of the page. Right? So charges on this side of that coil are going to be pushed into the page. Charges on that side of the coil are going to be pushed out of the page. That is going to force a current to go around it like this. Out of the page, into the page, out of the page, into the page. All right. So you can say anti-clockwise when viewed from below, because if you're lying under this thing, you would see it going anti-clockwise, or you could say clockwise viewed from above. Right? Or you could just say the charge marked A, again, add things to the diagram, it's fine. The charge marked A would be experiencing a force into the page, an EMF into the page. And the charge marked B would be experiencing a force out of the page. Right? Excuse me. So you have to establish that first. That's part of your answer. You've probably got 2 marks just. So the question is, which way is this needle going to go? Right? All right, well, if A is going into the page, then A is going away from X, right? It's going that way. Right? It's going to end up going down. It's not going to go up towards X. This is the way down. Right? So if A is going into the page, all of the other charges are going to agree with it, and that's going to create a current that goes in the direction from Y to X, right? When it's inside the galvanometer. And the information in the question said when it goes from Y through the galvanometer to X, the needle moves to the left, so the needle moves to the left. All right, so that's what you have to say. There are 4 things you pretty much have to say. You have to establish a right-hand rule for this. You have to pick any charge, like one there on one there. Doesn't matter which one. You can even pick one there and have the magnetic field lines coming out of the page, but that's just a little bit more difficult to explain. I think this is fine. Pick one of them. Establish, because of the right-hand rule, which way it's going. Link that to the way the entire current will be going in the circuit. Then zero in on the galvanometer and say, therefore, it's going from Y through the galvanometer to X, and then go back to the question and say, well, the question said if that's happening, the needle's going to the left. Right? They're the dots you have to join. Big question, that one. And if that's not enough, now you've got to graph it. Okay. It says, this is part B, the magnet oscillates. The magnet oscillates between the position shown in figure 3 and the position shown in figure 4 over 2 cycles. All right, where are we starting? Where are we finishing? Starting at the top, finishing on the bottom, right? So it goes 3, 4, 3. That's 1 cycle, 4, 3. All right, so it starts up and it goes down, up, down, up. Okay, so that's what's happening. The time taken to go between the position shown in figure 3 to the position shown in figure 4 is ½ a second. On the axis provided below, sketch the variation of the current through the galvanometer versus time t for the two cycles include a scale on the horizontal axis. Okay, how do you do this? Now, firstly, you have to remind yourself that you only get a current through here when the flux is changing. You only get a current here when these magnetic field lines are moving. If it's just sitting there, if the magnet was stationary, nothing would happen. You just put a magnet near some wire, you don't get a current in the wire. If you move it, right, and thus change the flux, you get a current, right? That's why that moving loop inside a magnetic field is a generator, right? If it isn't moving, nothing happens. So it's only when it's moving. So at the extremes, at the positions shown in figure 3 and in figure 4, it's actually not moving. It's actually doing a U-turn, and it's just stopping at point 3 and stopping at point 4. Right? So if it starts at 3 and it goes down to 4, it starts with no current at all. So here's what you're going to have to draw. Has to start with none, okay? So it's current, time, seconds, okay. Halfway between figure 3's picture and figure 4's picture, when it's halfway down the descent, that's when it's going to be going as fast as it's going to be going, okay? So that's when the current is going to be maximum. That's when the magnetic field lines are going to be racing past these wires and making the fastest current, or the most current, right? So you're going to end up getting this. Handy to know how to do a sine wave reasonably neatly. All right, so it's going to start at position 3. So that there is the position in figure 3. That there is the position in figure 4. That's back to figure 3. That's back to figure 4. That's back to figure 3 again. So on the way down, it speeds up on the way down, speeds up and speeds up. As it speeds up, the amount of current increases and increases. It reaches a peak when it's halfway down, and then it starts slowing down and slowing down as the spring starts grabbing it and holding it. Right? At the extremity, when it gets to here, it gets back to not moving for a certain amount of time, for a very short amount of time, and that's when there's no current. Then it starts being pulled up again, and the current starts being generated again. However, because the magnetic field lines are moving the other direction, they're going up, not down, the current is going to be reversed. Right? And then that is going to happen twice. So horizontal scale, they said put a horizontal scale on this. They said the time taken between where it is in figure 3 to where it is in figure 4 is half a second. So in other words, from there to there is half a second. So it already says time seconds. They've put that there for you, sorry. So you're just going to go 1, 2, that'll be fine. Okay. You can also go 0.5 and 1.5 there, but that'd be fine. Just make it obvious that they are the sort of tick points right there. Okay. They are 7 difficult marks to get. All right. Question 5. This is much easier than question 4. Okay. Circular coil of wire, 6 turns in the coil, diameter of 4 centimeters, connected to a voltmeter, so you can read volts, and there's a magnet nearby. A magnet is placed close to it. It isn't moving, it's just put there. Right? As the magnet is pulled away from the coil, so someone's going to whip it away, right? The magnetic field experienced by the coil varies according to this graph. So while it's just sitting there right at the beginning, it has a magnetic field strength of 0.2 Teslas. The coil is feeling a magnetic field strength of 0.2 Teslas. So maybe right next to the magnet it's even more. Right? Obviously, as the magnet goes away, that gets less and less and less, and eventually it goes down to 0 when the magnet is way out of reach, way out of range. And this is how it's a linear, it's a linear relationship. All right. And it says, part A says, show that the magnitude of the flux experienced by the coil for the position shown, this is before it's moving away, is 2.5 by 10 to the minus 4 Webers. Okay, flux is BA, right? And in that position, that's the beginning of its trip, right? The B is what it says at the start of the graph, 0.2. So it's 0.2, and the A is the area of that circle, right? Diameter 4, which means radius 2, but that's in centimeters. It has to be in meters, so you're just going to go pi r squared for a radius of 2 centimeters, right? So down here you're doing pi r squared, radius of 2 centimeters, and you end up getting, I think it's, yeah, you end up getting to two significant figures, 2.5 by 10 to the minus 4 Webers. Okay, easy enough. Right, 6b, determine the magnitude of the average EMF experienced by the coil as the magnet is pulled away from the coil over time. Okay, right, EMF in circumstances like this, EMF, oops, geez, I can't draw that funny Greek E, equals the number of turns in a coil, right, or a loop, multiplied by delta flux, delta time, okay? And you're going to get that from the graph, and you're going to get that because they told you there are 6 turns, okay? Getting this from the graph, just going back to the graph, this is flux versus time. The change in flux in that time, it lost 0.2 Teslas of magnetic field strength. Sorry, pardon me. Wrong thing. It went from 0.2 Teslas of magnetic field strength down to 0, and that means that it would have lost all of that flux that it had. It started off having 2.5 by 10 to the minus 4 Webers of flux, and by the time the thing got pulled away, after 1.5 seconds, that was down to 0 flux. All right, so delta flux over delta time is that divided by 1.5 seconds. So, plug it in. 6, 2.5 by 10 to the minus 4, 1.5 seconds, get the answer. Fairly straightforward. Okay, C, this is another modification. One of the game they've said to the apparatus, right, shown in figure 5. Using the same magnet, so you can't even change the magnet, that would enable the coil to experience greater EMF as the magnet is removed. Use physics principles to justify the suggestions. All right, excuse me. So you can either increase the number of loops in the coil. I mean, this is the formula we're using, okay? That's the EMF. So if we're going to get that number bigger, right, you can either increase the number of coils or increase this rate. You can move the magnet away faster. That's about it. You could increase the area of the loops because flux is BA, right? You can't change the B because they said you can't change the magnet. So the only things you can change this, or you can change that. And when you realize they said apparatus, that's probably the only 2 things you can actually change, because that's changing the apparatus and that's changing the apparatus. It's actually rebuilding the thing differently, right? You can also move the magnet away to make this ratio a bigger number, right? Loses the same amount of flux in less time, but that's not really a change to the apparatus. That's a change to what the apparatus is doing, okay? Okay, question 6 is the diagram for question 6. I'm just going to label it here, 12 volts RMS. Okay, a group of students constructed this model of a power transmission system using circuit shown. Right, long distance wiring has a total resistance of 5 ohms. The circuit has got 2 ideal transformers. They're identical. One of them's backwards to the other one, right? One of them is a step up, 1 to 10. One of them's a step down, 10 to 1. Excuse me. Okay, the transformer terminals are labeled P, Q, R, and S, and I just haven't put that there. P and Q over there, R and S down here. There you go. Okay, the voltage across the globe is 11.5 volts RMS. Okay, so if you put a voltmeter across here, which I've just realized is out of screen, that's 11.5 volts RMS. Oops. All right, let's check out the questions. A, determine the potential difference across PR. Right, so if you put a voltmeter there, what are you going to get? Right. And across QS. Right. Show you're working. Okay, here's how you do it. The first one's pretty easy. That should be 120 volts. 12 volts RMS on this side. 10 times as many coils on this side of the transformer. Step up transformers step up the voltage. They're named after what they do to the voltage. So this is going to multiply the voltage by 10 times. So if it's 12 volts on that side, it's going to be 120 volts there. So the voltage across PR equals 120 volts. You can either use that explanation, or you can do what what the solution did, which just applied the formula, right? VPR, V primary over V secondary equals N primary after over N secondary. You can do that. All right, either way works. Now for voltage across QS, you literally do the same thing because you already have the voltage across the light globe. And because both of these are sorry, what was the word? Pardon me. I was going to say perfect, but the word is ideal. But because both of the transformers are ideal, they are assumed to have lost no power from one side to the other. So they're not going to lose no power from one side to the other. So if the voltage on this side is 11.5 volts from there to there, it'll be also 11.5 volts from there to there, right next to the transformer. So it's going to be 10 times as much over here. So VQS is going to be 10 times that, which is 115 volts. So that's part A. And part B is how much power is supplied to the globe. You already know how much voltage. You need to figure out what current is supplied to the globe. So this is how we do it. Now the power across the globe is going to be the same as the power across QS, again, because that's ideal, right? So IR, excuse me, pardon me, not IB, not IR. Power across there is going to be the same as the power across here, right? However, the power across there is going to be a little bit less because there's this resistance than the power across here. So we need to sort of take that into account and figure out how much that resistance has cost us. And the shortest way to figure out that is to use V equals IR for here, for this section here. Right. So the voltage drop from there to there, how many volts has been used from there to there, excuse me, is 5. That's 120 minus 115. Right. Potential difference is 120 here, it's 115 there, so somehow 5 volts has been used there. All right. I times the resistance, 5. So therefore the current is 1 amp. All right, we're halfway there. Now to find the power across QS, I'm just going to work over here now, sorry. To find the power across QS, which will equal the power across the globe, we need to factor in the fact that this has caused it to lose some power over here, right? So the power across QS is going to be VI, which is how much power is being supplied over here, minus I squared R, and that's the formula for power loss over power lines. So we're just going to fill all this in and make sure we've got the right figures. Excuse me. All right, over here, VI, V here is 120, I is 1, we just found out what the I was, minus, I is still 1 squared, times the resistance, which is 5. All right. Work out what that comes to. It's 120 minus 5, it's 115 watts. So therefore the power across the globe is 115 watts. 115 watts there, 115 watts there. 120 there, 120 there. 5 watts gets lost in transit. Question 7, I might zoom this in a bit. Yeah, that's okay. All right. Question 7, every time I see this sort of roller coaster thing, it's almost certainly a conservation of energy question. Okay, a car weighing 20 grams starts from a height of 2.2 meters above the ground, travels down the track. Right. The crest has a circular profile and a radius of 0.5 meter. Point A on the track is 0.5 meter above the ground as shown. Okay. The track and car system is frictionless and you don't worry about air resistance. Fine. Determine the speed of the toy car when it reaches point A. Show you're working. Okay. It is at rest. It's not moving up there. So the only energy it has is gravitational potential energy. So that's mgh there. Down here, it's moving as well, and it still has some height, so it's got a gravitational potential energy and kinetic energy, right? However, the total of those two will add up to that one because the total amount of energy that the car has at any point should stay the same. Right? So total energy at the top equals total energy at point A, and we're basically going to solve that and find what's missing. All right, so you're going to go mgh at the top equals mgh plus 1/2 mv squared. That's the formula for kinetic energy. All right, and you put the put everything in. In fact, you can take the m's out if you really want to simplify it, and you're solving this whole thing for v. Excuse me. You end up getting the velocity as 5.8 meters per second. And the fact that you took the m's out is why I didn't mention that you had to convert that to kilograms, because you don't. It doesn't even turn up in the formula. All right, 5.8 meters per second, that's the answer to the first one. Part B, it says, does the toy car leave the track at the top of the crest? Support your answer with a calculation. All right. At the top of the crest, just hang on a minute. One crest. Here's the car at the top of the crest. If it just leaves, then its acceleration is just gravity. It's 9.8 meters per second squared. If it is not quite leaving, if it's going over slower, right, still going in that circle, then its acceleration is firstly 9.8 plus the acceleration plus the force that keeps it in a circle. All right. But if it's just not quite taking off, right, then the only thing that's forcing it to be down there is gravity, and that's the acceleration of 9.8 meters per second squared. Okay, so from this, you're going to get a fairly simple formula, right? The formula for centripetal motion, the motion that holds something in a circle, is F equals mv squared on r equals mv squared on r. And because F equals ma, that part is the a. So a is v squared on r. In this particular case, the a happens to be g, the acceleration due to gravity. So g is v squared on r for something that is just sort of floating its way around the circle, not quite leaving. Therefore, v is going to be the square root of gr. Right. If that's not on your cheat sheet, it's probably worth sticking it on, right? Rather than having to wait and do all that sort of stuff. You'd get it anyway, right? But you may as well use the shortcut. Just put that shortcut in your cheat sheet. Okay, so if you calculate this, you get 9.8 times 0.5, I think, wasn't it? Yeah, 0.5, because that was the radius of curvature of those humps, of those crests. And you end up getting that the v is 2.21 meters per second to just make it around the circle. Any faster and you're going to leave, right? You're going to take off. Any slower, it'll be fine, right? However, we know from this diagram that because that's half a meter high and that's half a meter high, the velocity at that point and that point are going to be the same. It's going to have the same kinetic energy at the same heights and the same, you know, the total energy up there is going to be divvied up the same way, right? So it's going to have the same v if it's got the same h, right? And so it will actually be going 5.8 meters per second over there. And if it goes any faster than 2.1 or whatever I said, it's going to launch. So it is definitely going to launch. All right. So does the toy car leave the track at the top of the crest? Yes, it absolutely does. Question 8. This is another fast one. It's worth 3 marks. This should not take 3 minutes. Ball swinging around, right? 20 degrees there. It's a horizontal, horizontal circle. It's a 1 meter long string. So you've got this right angle triangle here. And that's 20 degrees and that's 1 meter. Right. The radius of the circle is r. The string is at an angle of 20 degrees. Determine the speed of the ball. Show you're working. Excuse me. All right. Velocity is displacement over time. Right. For one circuit, it goes around 2 pi r divided by the period. Right. And the period of rotation is 1.95 seconds. Right. So we can just cross that out and go 1.95. So there's your formula. You don't know the r, but you do know that that's 1 meter and that's r. So you're going to do a bit of grade 8 trigonometry there. And so, r is going to be what? It's going to be 1 sine 20, I think. Right? Sine of 20 is r on, yeah. It's going to be the sine of 20. So r is easier to get hold of. throw it in, get V, easy. That should take you 1 minute. That'll save you a bit of time. That's a quickie. It's always good to get a quick question out. All right, question 9, everyone's favorite, projectile motion. Golf ball is launched from an unknown height above the ground. It lands at a horizontal distance 2.35 meters away. Wasn't much of a shot. As shown in figure 10, vertical and horizontal components of the velocity as it landed are shown in the landing position. Okay. Show that the time the ball spends in the air is approximately 1.57 seconds. Okay. Well, it went horizontal figures go together, vertical figures go together. We've only got one vertical figure apart from the acceleration, which is 9.8, right? But we've got two horizontal figures. Right? We've got the distance and we've got the velocity, right? Velocity equals displacement over time. We're trying to find the time, right? So time is displacement over velocity, which is 2.35 meters at a speed of 1.5 meters per second horizontally. That doesn't factor into it. That comes to 1.57 seconds. All right. Determine the launch speed of the ball. Show you're working. Excuse me. Okay. You need to determine the horizontal. This is what we're going to do. You need to determine these two things for up here and then add them together to find the actual sort of hypotenuse launch speed. Okay. You already know one of them. Horizontally, there is no acceleration, right? So if it landed going horizontally at 1.5 meters per second, then it took off that way as well. So it was initially moving sideways at 1.5 meters per second. So that's half the job done. We just need to find out what the hell that was. Okay. So vertical figures. What have we got? Its final vertical velocity was 9.5 meters per second. And we're going to put a negative on that because it's down. Given that it started going up and finished going down, positives and negatives are going to matter here, right? Which means the acceleration is negative 9.8 meters per second. The time it was in the air for is 1.57 seconds. And we're trying to find u. V equals u plus at. So we're going to use v equals u plus at. Make sure you put the negatives in where they belong, right? Do the algebra right, and you'll find out what u comes to. It turns out that u comes to 5.89 meters per second. Going up, it should be positive, right? Because it's started going up. If you get a negative answer, you know you've done something wrong because it's going up. And the last thing you need to do is resolve those two vectors. Sorry, not resolve them, add them. You need to add the horizontal 1.5 to the vertical 5.89. Just a bit of Pythagoras. That squared plus that squared, square root of your answer, and you should get 6.1 meters per second. All right. Another reasonably fast one. That's not going to take too long to do. You just needed to realize quickly what to do. Question 10. This is the last one for this recording. A toy cart of mass 100 grams has a spring-loaded launch mechanism. There's a spring there, there's a steel ball that weighs something, and when the spring pushes the ball out the back, the car's going to go forwards. All right. Steel ball of mass 20 grams is loaded into it. That's shown. All right. Spring has a spring constant of 800 newtons per meter. The spring is compressed by 1 centimeter with the ball against it. Okay. The cart ball system is not moving at the moment. A graph of energy versus spring displacement is shown in figure 12. Okay, so when the spring is displaced by 0.01 meters, which is 1 centimeter, it has that certain maximum amount of energy in it. We don't know what it is yet. They didn't give a vertical scale, but that's the maximum, right? And of course, when it isn't compressed at all, it has no energy in it, right? So when the ball isn't there and it's just going dangling and sitting there a centimeter longer, no energy. All right. The spring is released and the ball is projected. Both the cart and the spring move. As the spring expands, no energy is released as heat or sound. So all of this goes to motion of the ball. On the graph above, Draw the graph of the kinetic energy of the cart ball system as the spring expands. Okay, the total energy of this thing has to stay the same, right? So it begins with no kinetic energy. Okay, so when the spring is compressed by 1 centimeters, there is no kinetic energy, right? So it's right there. This is my line for kinetic energy. It's going to go in. In fact, I'm going to do it in pink. I don't care. Okay, so 0 kinetic energy when the spring is compressed. When you hit the trigger and let it go, as the energy leaves the spring, it goes into the trolley as kinetic energy, but the total will have to stay the same. So the total amount of energy is that, right? So all the way along, the total amount of energy, which I'm going to put in blue, is there. Right? Doesn't change. Energy can't come from somewhere else and it can't be destroyed. It wasn't being wasted as sound or whatever, or heat, right? They told us that. So in order for another graph line to be on this thing so that the sum of that and this other graph line always comes to the same figure, I have to pretty much do a reflection of this. So it's going to end up doing like this. So at any one stage, at any point, that point plus that point will add up to the blue. That plus that will add up to the blue. The two heights, the two amplitudes will add up to the blue line, right? The blue line is the total energy of the system. It's the addition of the kinetic energy and the elastic potential energy that it has, right? When there is no elastic potential energy left, when the spring is completely sprung, that's the instant where the trolley is going at its fastest and the kinetic energy is maximized. And that's why it looks this way. Now, they also said put a scale on this. We've got to figure out how much kinetic energy it's got or how much of something it's got, right? We don't have enough figures for kinetic energy. A half mv squared, we don't have the v, right? But we do have the figure for elastic potential energy. We've got enough for that. We've got the K and the X, all right? So elastic potential energy equals a half kx squared, which equals a half times 800 times 0.01 squared. Once again, get the units right. That comes to 0.04 joules. So that is the maximum amount of elastic potential energy that this thing ever has, which is up there. So that point here is 0.04 joules. They've already written joules there. So make the rest of it happen. Half of that, 0.02, 0.03, 0.01. They've already got the units. You're finished. All right. Part B. Explain using physics principles your reasoning for the scale for the y-axis chosen. Now, they're not asking you to explain your reasoning for the pink line, right? Don't waste your time saying that. They didn't ask for it. It's not going to give you any marks. Don't do it. They're asking about this, the scale. All right. Using physics principles, your reasoning for the scale for the y-axis chosen in part A. They're basically asking you to say that this has to be the total energy, even though you've only calculated elastic potential energy, right? Because when the cart is stationary, that's when the elastic potential energy is maximum, and because there's no kinetic energy there, there's no other form of energy. The elastic potential energy has to equal the total that it's ever going to be, right? And so you had the means to find out what that came to, and that gave you the number, right? And the rest of the explanation is that, and therefore you drew the rest of the scale to make a number line on the side. That's about it. Okay, that's the end of this video. There's our fourth video coming up fairly soon, and that's going to have questions 11 to 20.